Okay, let's get started. So today I'm going to be recording this lecture because this will be for my Monday, Wednesday group because I'm not going to be available Wednesday or Thursday, I guess Friday too, since the campus is closed. So I'm going to have to be careful walking around here because I'm tied to a cord, okay, for a microphone. And hopefully this works out well because I have to look at the PowerPoint and the screen, and I can only see one at one time. Or not the screen, but the video and the PowerPoint. I can only see one at one time. So hopefully this works out okay. Just a few announcements. The homework is actually due Wednesday. I mean, the 11th, sorry. It's due on the 11th. Make sure you have read chapter 11, not 10. Okay? So I'm going to be walking around kind of carefully because I'm worried I'm going to trip or something. Okay, and my range of motion is going to be at this border because I don't have a camera person. Okay, it's just right there. So, okay, I want to continue our discussion from last time, and let me fix this cord. So last time we talked about. We introduced the more formal definition of torque. And we said that torque is a cross product. Okay? Torque is a cross product, and there's a nice way to evaluate this cross product by evaluating a determinant. And you set up the determinant by writing your first row in terms of the I hat, J hat, K hat. The second row, the components of R. And the third row are the components of F. And then you go through and evaluate this component by component, and you get the value of the torque. And I got to remember, because I'm recording, I can't use red or green. I'm limited because they don't show up in videos. Okay, sorry about that. Okay, so I want to do an example where I calculate torque. So we're given this case where the force is 3I plus 2K, and R is I minus 2J. So let's go through and calculate the torque on this particle. Oops. So we're given F is 3I plus 2K, and R is I minus 2J. And again, just as a review, I want to go through and evaluate this thing. So I'm going to set up my determinant. And I'm going to put the components of R in the second row, which is going to be 1, negative 2, 0. And then in the bottom, I'm going to have 3, 0, 2. And remember, the way we do this by components, we have to cross out the top row. If you want the x component, cross out the top row in the first column. And then you take this times this minus that times that. So let's do this. Okay. The middle, the J component or the Y component, cross out top row and the middle column, and you do 1 times 2 minus 3 times 0. But the middle term, you have to put a minus sign do this right. And then the last term, the k hat term, by the way, the even numbered columns is always a minus sign. So if this was a four-dimensional problem, which you deal with in relativity, the fourth column would be also have a negative in front of that term. Cross out the top row, last column, and we get 1, -2, 3, 0. And so the x component is -2 times 2 minus 0 times 0. What's -2 times 2? The j hat term is going to be, I'll put a minus sign there, 2 minus 0. It's 2. And then the last term, 1 times 0 minus a -6. 0 minus a -6 is +6, right? And that's your torque vector. All right? That's how you calculate the torque. That's how you calculate the cross product. I'm going to introduce the concept of angular momentum. It's the cross product too. And so you would evaluate it the same way. Okay? Questions on that? Pretty straightforward. Okay. Let's do this next problem. I just want to make sure my video is okay. Just 1 second. Okay. I notice purple doesn't show up well, so I'm not going to use purple anymore. Next question I have has to do with how we calculate torque. You can calculate the torque about any reference point. Oops. You can calculate the torque about any reference point. And so I want to calculate the torque in this particular problem. We have a particle moving to the right along the x-axis. So let me draw a picture. I think I'm going to be limited to blue and black. I got to find my black marker, which is right here. Okay. Let's say V is this way. And so the particle's going like so. And there's a force acting on it. We'll call the force F, okay? And that force is the kinetic frictional force. I can calculate the torque about this point, or I can calculate the torque about this point. And let's say this point is a distance b above the origin. So this distance is b. And in the first case, I want to calculate the torque about the origin. Okay? So let me draw my r vector. It goes from my reference point to the point of application of the force. Let me define my coordinate system. Let's do it this way. And so it's really traveling in the y direction, not the z direction, based on the way I just defined my coordinate system. So we can say v is v naught j, and r is, we'll call it r sub y j. If I calculate the torque, I'm going to have r sub y times j cross v naught j. What does that cross product give me? Well, be careful. It's j cross j. What's j cross j? So let's do it this way. If we don't remember, the magnitude of the torque is the magnitude of the r vector, the magnitude of the f vector, times the sine of the angle between them. What's the angle? The angle's 0, right? Okay. The two vectors are parallel, and so this torque is 0. Okay. If the vectors are parallel to each other, then the torque has to be 0. And the reason why is because there is no unique vector that is perpendicular to two vectors that are parallel to each other. Okay. Now let me do the same thing, but pick that as my point. This point up here, we'll call point B. What does my r vector look like? My r vector goes from my origin to the point of application of the force. This is the angle between the two. So let's do some of the torques about point B. So we would take, the torque would look like this. Oh, we have to write down what r looks like. Isn't the r vector, isn't r sub b look like this? It has a component in the z direction. And a component in the y direction. Isn't it true that that's the vector? Oh, I made a mistake somewhere. Where's my mistake?
It's from the z to the y.
But what's wrong with the z component that I drew? It should be negative. So the torque then is going to be b times k hat plus r sub y times j hat crossed negative b. Thank you. I keep forgetting the darn negative signs. Sorry. So what's j cross j? So my torque then is minus b times k hat cross f sub k times j hat. So what's k cross j? Well, what I would do is the following. X, Y, Z. I pick my fingers pointing towards the k hat direction, and I need to curl them towards the y hat direction. Oops. Did that wrong. Points into the board. Right? Point my fingers this way, curl them this way, points into the board. In the negative I direction, right? But there's a minus sign in front. That's the torque. So the torque is different depending on where you choose your reference point. You choose your reference point really out of convenience for you. If you want to study a system, you want to make sure that the reference point that you choose makes the problem easier, not harder. And that's going to be important in chapter 12 when we do equilibrium problems. When we do equilibrium problems in chapter 12, you want to be able to choose your reference point to make the problem easier. For example, to have less unknowns in your equations. Okay? And that'll make life easy for you. Question?
Could you explain that right-hand rule that you did again?
Okay, so I'm going to point my fingers in the direction of the k-hat direction, but I got to curl them towards this. So I can't do it this way. I have to flip my hand around and do it. Okay? All right. Let me go change slides. And I want to do it by hand because of my video. Oops. Okay, so here are some properties of the torque vector. In fact, these are properties of cross products in general. Okay? If you take the cross product of two vectors, the cross product is not commutative. That means that when you take A cross B and B cross A, you don't get the same thing. Right? If you do one, in arithmetic, if you do 1 plus 2, that's the same thing as 2 plus 1, right? That's not the case for cross products. Okay, A cross B is minus B cross A. They're negative of each other. And I actually established that the other day when I did I cross J, J cross I showed you what they are when I used the right-hand rule. Additionally, it does obey the distributive law. Okay, just like in, I guess like in algebra. If A cross B is 0, that tells you the two vectors are parallel. Okay? Conversely, if the two vectors are parallel, A cross B is 0. Okay? If A cross B is C, C is perpendicular to both A and B. And then the last thing, A cross B, if A cross B equals C, then C points in a direction from which the rotation from A to B appears to be counterclockwise in a right-handed coordinate system. I'm not going to say anything more about the properties of the cross product. You'll learn them in Calc 3. Okay? I want to introduce to you another concept. And like I said before, I'm going to show you slides that look like this to draw the analogy between translational and rotational motion. For kinematics, we had x, v, and a for translational motion, theta, omega, and alpha for rotational motion. For dynamics, we have Newton's second law for translational motion, and then we have the analogy to it, the sum of the torques equal I alpha for rotational motion. We also had equations for translational kinetic energy and rotational kinetic energy. What about momentum? Okay. There is a quantity that's associated with the rotation of the position vector. Okay? It's the rotation of the position vector of a particle with linear momentum p. It's not really a natural quantity like linear momentum because we define its direction. We choose it by convention. And we use the right-hand rule. And we define the angular momentum as the cross product r cross p. So in this particular problem that I have up here, we have a particle with momentum mv going that way. Okay? As this object goes that way, what happens to this vector? What happens to this angle that's described by this vector? It gets smaller. The angle changes. So this thing is rotating, right? this vector is actually rotating. But the vector here, if we choose this point to calculate the angular momentum, is that vector rotating? No. So again, here the angular momentum is going to depend on how you choose your reference point. And it really represents how this vector is rotating for a given linear momentum. And again, the angular momentum, we use the letter L, is perpendicular to both R and P. And if P, R, and L are perpendicular to each other, they will actually form a right-handed coordinate system, like an XYZ coordinate system. So we do have a right-hand rule for this. It's the same thing. You point your fingers in the direction of the R vector, and curl them towards the momentum vector. We would have to evaluate the determinant like we do for torque to evaluate the angular momentum. So what are some applications? Well, we can apply this to gyroscopic motion. For example, the bicycles. And I will do a demonstration with a bicycle wheel later on today. The Earth's precession. Spinning tops. Now granted, when you start dealing with gyroscopic motion, it does get complicated. But for some very simple cases, we can talk about them. And I will do one simple case today regarding gyroscopic motion. We can talk about the physics of figure skating. And one of you folks is going to demonstrate that later on today. Although you're not going to be figure skating, you're going to be sitting in this chair, and someone in the class is going to spin you. Also, when you look at atoms, one of the quantities that's used to describe the electron in an atom is angular momentum. Those of you at chemistry, you hear about the s orbital, the p orbital, the d orbital. They represent the angular momentum of the electron in the atom. It's conserved in the atom. And so you can describe the electron in the atom in terms of its angular momentum and also its energy. There's also another kind of angular momentum in quantum physics that has no classical analog, and that's called spin. And there's really nothing, there's no analog classically to describe spin. It's just intrinsic. It's an intrinsic angular momentum that the electron has. Let's consider the angular momentum of a particle going in a circle. So our particle is right up there. The red dot. I've drawn the R vector. Of course, V is tangent to that, right? V is tangent to the circle. And so that means M is tangent to the circle. So maybe I should draw that. I'll draw it from a different point of view. Let me draw that again. This will show up better on the video. So let's assume the particle's here. V is this way. And R points this way. Which way does the angular momentum point? What is it? Out of the board, right? Right? Again, just draw. I always like doing it this way. Here's R. Here's P. Take your fingers, point them towards R hat, curl them towards P. In my picture here, the angular momentum points towards us. out of the board. Okay? So here, L is out of the board. What is the value of this thing? Well, L is R cross P. The magnitude of L is the magnitude of a cross product, which is given as the magnitude of R times the magnitude of P times the sine of the angle between the two vectors. What's the angle between those two vectors? 90, right? And the r vector, the magnitude of the r vector is just the radius of the circle. P is mv. And that's the magnitude of the angular momentum vector. Now, V tangential is r omega. So let's substitute that in here. What is mr squared? It's the moment of inertia of a point particle, right? So we can write angular momentum as I omega. I'm not proving it in general, but you can see for a point particle, it's mr squared omega, where mr squared is a moment of inertia. But in general, the moment of inertia is I omega. Now, I didn't write that as a vector, okay? This relationship is only true when these two are parallel to each other. I'm going to show you an example when they're not parallel to each other. Okay? So generally, when they're parallel to each other, we define this along the z direction. We define the direction in which omega points as the z direction. Okay, oops. So we can write the magnitude of the angular momentum this way. But if we know I, we can write it as I omega. But this only works when this is parallel to this. If it's not, then you can't write this down. It turns out that if it's not, I is actually a matrix, a 3 by 3 matrix. Don't worry, we're not going to do problems like that, okay? But you can always use this to calculate the angular momentum. This is always valid. This is only valid when these are parallel to each other. Okay. So L sub z is I omega. The z-axis is chosen by convention. And it's not a vector equation. Okay? It's only a vector. It looks like a vector equation when these two are parallel to each other, but it's not a vector equation. I is generally a 3 by 3 matrix. And we're not going to get into the details of that in this course. Part of the reason why it's not true in general is that when you look at the rotation about an axis, it's not you're not going to have symmetry, or you're going to lack some symmetry. So I'm going to give you an example. I'm going to do the same circle, object going in a circle, but I'm going to calculate the angular momentum not about the center of the circle, but a point out of the plane of the circle. This is a little bit harder. So I'm going to calculate the angular momentum outside the plane of the circle. And I'm probably going to use the PowerPoint to elaborate on this because I'm going to do a really bad job making pictures. Okay? I'm not the best artist. So I really rely on PowerPoint. And let me get a pointer. Just give me a second. So here's the object going in a circle. It's a horizontal plane. And I'm choosing a point below the center of that plane, below the center of that orbit, a certain distance below the orbit. My r vector points from my reference point to where the object is at that instant in time. So this is the r vector. Okay, the momentum vector points that way. The r vector has 3 components. Okay? This r vector has 3 components. Let me draw a coordinate system to illustrate this. I'm going to choose a point down here. I'll draw the circle like this. As best I can, okay? I say the particle's there. Let's draw the momentum this way. Actually, let me draw the momentum this way. Oh no, this is fine. Let me write down the r vector. These 2 components are in the plane of motion. Do you guys see that? The x and y components are in the plane of motion. I purposely drew this so the plane goes through the origin. And then this is not in the plane of motion. What about the momentum? The angular momentum is within the plane of motion. The angular momentum has an x component and a y component. And instead of writing it as m times v, I'm going to write it this way. This is mv sub x, this is mv sub y. Less writing for me, okay? Now I got to take the cross product. So this will be fun. Here comes the I hat term. Cross this and cross that. What am I going to get? Yeah, let me write this. Yeah, actually, let's do it that way. Let's do it quickly. We're going to get this times this minus that times that, right? Right? What about the j hat term? It's going to be this times this minus that times that, right? And what about the last term? Okay, so this times this minus this times that. So this term is in the plane of motion. This term is perpendicular to the plane of motion. So it has two components. One in the plane of motion and one perpendicular to the plane of motion.
Did you write K hat twice there or right after?
Oh, for this one?
Yeah.
Wait. RXPY.
The K hat?
Oh, I wrote, okay, I'm sorry. Thank you. So there's two components.
Is the first one not negative?
This one?
Yeah.
Oh yeah, it is negative. Thank you. So this is in the plane of motion. That's perpendicular to the plane. It's along the z direction. Okay? So that's why when you look at the L that I drew in the picture up there, it points in that direction that you see. Of course, what happens to that? That thing constantly changes direction. The z component doesn't change direction, right? When you see that thing going in a circle like that, the z component stays the same. In fact, the z component stays constant. Its magnitude stays the same, and its direction stays the same. And since omega is constant, the magnitude of the components in the plane stay the same, but what's changing is the direction. Okay? So now L is a lot more complicated. Let's say something about this problem. I want to look at the motion of that object between the 2 points shown, from here to here. Okay? Let's assume omega is constant. It's just going in a circle at a constant speed. I want to look at a top view of this. Now remember, the z component never changes. Only the component of the angular momentum in the plane changes. Top view. Okay? We're going to go from here to here. Let's assume this angle is small. Isn't it true that delta r is 2r sine of theta over 2? Where that radius, this distance, is this length times the sine of phi. Isn't that true? Right? Here's a hypotenuse. This is opposite the angle. So this r is just the magnitude of that big vector r times sine of phi. Now, for small angles, delta theta over 2, I'm sorry, sine of theta equals theta, right, for small angles? For small angles, sine of theta equals theta. Everyone remember that or not? From Calc 2. I can't use that color. Have you ever done the expansion of sine of theta? Taylor expansion? Yeah. The first term is theta, right?
He's used x, yeah.
And the first term is theta. The next terms are going to be, the next term is order of theta cubed.
Yeah.
That's too small. We ignore it. Right? Take take the sun, the sine of 0.01 radians, and you'll get approximately 0.01. Okay. So what I'm saying there is sine of delta theta over 2 is approximately equal to delta theta over 2 in that picture up there. Okay? So if I do the substitution up there, then my delta R is just R sine of phi delta theta. Let me divide by delta t, and I get delta R over delta t is R sine of phi delta theta over delta t. What's delta theta over delta t? Omega. Okay. So in the limit as delta t goes to 0, this is omega. So dr dt is R omega sine of phi. What does that look like, that product? That little r is the magnitude of that vector. Right, this distance, the distance from here to here, and the distance from here to here doesn't change as it goes in a circle. I have the magnitude of one vector times the magnitude of another vector times the sine of the angle between them. Doesn't that tell you cross product? And so V is omega cross R. Now if you think about it, V is this way, R is this way, or this way, but I'm focused with this component in the plane. Which way is omega? Let's do the simple case. Let's choose a point in the plane. Which way is omega? Object's going this way. Doesn't it point out of the board? Okay. Omega's this way. R is this way. What's omega cross R? Isn't it that way? So the cross product of omega and R is in the direction of the velocity vector. The magnitude is R omega sine of phi. So it's true in general, then we can write the velocity vector is omega cross R, which is not derived in this book, but for me it's nice to talk about. For all the problems that we do in here, guess what? R and omega are perpendicular to each other. Okay. Let me do an example involving angular momentum. What time is it? 2:45. Okay, I got mixed up because that thing wasn't changed. I was like, whoa. Okay. So we're given the position of a particle of mass 3 kilograms is given by that expression. I want to determine the angular momentum of the particle about the origin as a function of time. Okay, so we're given R is equal to 6I hat plus 8tj hat. We want, and we're given M, is 3 kilograms. We want L, So that's going to be 6I plus 8TJ. What's P? How do I get P now? Well, P is M times V, right? Okay, so it's going to be 3 kilograms. What do I put for V? So I take the derivative of this with respect to time. What does that give me? Right? Okay. So let me simplify this a little bit. What's J cross J? 0. So it's just these two terms. And 24 times 6 is 144. Well, what's I cross J? Okay, well, then let's do this. I'm not going to set up the determinant to do that. I'm just going to use the right-hand rule. That one's too simple. Oh, I got to curl my fingers towards J, right? I put my fingers in the direction of in the X direction, but I got to curl them this way. So I got to rotate my hand and then curl it. My thumb points upward. That's in the K-hat direction. And what are the units for this thing? It's kilogram, meter squared per second. That's the units.
So you can just basically take the constants out and just put them to the front?
Yeah, because it obeys the distributive law.
Okay.
Because the constants are just numbered. They're not going to affect, they're just going to affect the magnitude of it, right?
Yeah.
I can't ask that question yet. I was going to ask a question that I haven't introduced the topic yet. Now, we also wrote Newton's second law as dp dt. Guess what dl dt is? The time rate of change of angular momentum. You can see it up on the board. The time rate of change of angular momentum is the torque. When you take the derivative of this, you use the product rule for differentiation. You take the derivative of the first term, cross the second term, which we have here, plus the derivative, I said it backwards. Derivative of the second term times the first term. So anyway, I said it's backwards. What's dr dt? And so you have velocity crossed mv. What's v cross v? 0. So this term is 0, and so you get r cross f. So the time derivative of the angular momentum is the torque. Okay? The time derivative of the angular momentum is the torque. Now we've introduced all the topics for rotational motion that we need to talk about. So dl dt is the torque, or the sum of the external torques is dl dt, which equals I alpha. In the case where the torque and alpha are parallel to each other. Let me do another example. I have a much harder one in the notes. I'm not going to go over it. You can take a look at it. I'm going to go back to the same example I had before. Okay? But this time I'm going to calculate the angular momentum. So let me erase this. We already calculated the torque on this thing. Let's go back to this problem. It's moving with speed v. What is L about the origin? Oh, sorry, across P. Here is the r vector. There's the v vector. What can you say about them? They're parallel, so the cross product is 0. And if L is 0, then guess what the LDT is? That's what we got before, right? Isn't that what we got in the previous problem? Now, let's calculate L about point B. If we want to calculate the angular momentum about this point, this is our vector. L is going to be what is that going to give me? These two terms cancel. What does that give me? What was this? What was that cross product before? Wasn't it with this one, right? Yeah. Now let's take the derivative of this. If I take a derivative with respect to time, I have a dv dt, right? What's dv dt? Acceleration. What's ma? Force. It's that frictional force. So I get the same thing again. So I have a much harder example with a dumbbell in the notes. I just have a FYI. You can take a look at it. That's the one where your angular momentum is out of the plane. Now, you are now in a position to solve pulley problems with 3 different techniques. There's an example in your book. So the video I'm going to make for next time, for Thursday, I'm basically going to focus on doing a bunch of problems. Okay? I'm basically going to focus on doing a bunch of problems. I'm going to do the pulley problems 3 different ways. Okay? So really what I'm trying to do is set myself up so that the next video I make is just a bunch of problems and for you to solve. Question?
Why are you able to just add them under the angular momentum about point B?
What do you mean add them?
Is negative b k hat plus.
That's this vector, right?
Okay.
Right, that's this vector in terms of its x and y component. No, in terms of its z and y components.
Okay.
Okay.
So that's supposed to be instead of a plus sign, that's a cross product?
No, this is, right, you write the components as the sum of two things, right?
Right.
Oh, this one. I'm sorry, you're right. Thank you.
Okay.
What if you have a system where there's no external torque? What does that mean? Well, it means dl dt is 0, right? No external torque means dl dt is 0, right? What does that say about L?
Conserved.
Yes. So we can have problems where angular momentum is conserved. Okay? And so we can do problems involving conservation of angular momentum. I'm going to do an easy one here. And in the video, I'm going to do a horrendous one where you have an object colliding, I'll show you this one, with a rod on a frictionless surface. And you have to conserve linear momentum, angular momentum, and energy. So I'll do that one in the video. I don't want to do that here. Okay? So what does it mean when angular momentum is conserved? Right? Your total L of the system beforehand equals the total L of the system afterwards. Okay. So let's say we have this person. There's 100 kilograms, runs at 2 meters per second, tangent 2, and then jumps onto the perimeter of a stationary merry-go-round. The merry-go-round has a radius of 2 meters and a mass of 50 kilograms. I want to treat the merry-go-round as a uniform disk. I want to find the angular speed of the merry-go-round in a man system. So we have this person running this way, jumps on. It's hard to draw this. That's not an accurate drawing. I have to draw it so the person comes out of the board, but I can't do that. Okay? So he jumps on the end, and they spin together. What kind of it's a collision. What kind of collision is this? It's what? Yeah, it's completely inelastic collision. Okay. I'm going to define my system as consisting of both objects. And I'm going to calculate the angular momentum about the center of the disk. You might say, well, Why do I choose that? I can calculate the angular momentum about any point. I can calculate the angular momentum about this point. I can calculate. Why do I choose that one? I call it the center of the disk, but it's the center of the merry-go-round. Why did I choose that point? What? Go ahead. Yeah, but why do I don't have to choose that pivot point to calculate angular momentum. I can choose any point. I'm free to choose any one, but why that one? That's true, but there's a force there, right? Isn't there a force at the pivot? Yeah, what's the torque if the force goes through the pivot? 0. Okay? If I choose a point where it's not at the pivot, there's going to be a torque about that point. Then I cannot use conservation of angular momentum. Okay, the force is right here. And so I want to choose my pivot point there so that the torque is 0. No external torque, angular momentum is conserved. So how do we write the angular momentum for that person? Well, the r vector is this. All right, here's the r vector, there's the p vector. Essentially this is the angle between them. If you take r times the sine of theta, what do you get? All right, because L is going to be this. What's r sine of theta? It's the radius of the disk, right? It's opposite. So it's going to be the radius of the disk. And so L that's the initial angular momentum of the system. Okay? So we want to say that the sum of the initial angular momentum equals the sum of the final angular momentum. Well, what's the angular momentum of the disk at the beginning? Well, it's not spinning, so it's 0. So my initial angular momentum of the system is just going to be that. So my initial angular momentum is just mvr. My final angular momentum of the system is going to be the angular momentum of the disk, the merry-go-round, plus the angular momentum of the person. And of course, we can write angular momentum as I times omega. They're both going to be moving with the same omega, right? And they're both going to be moving counterclockwise, clockwise. So should I put minus signs all the way across here? Why not? Well, number one, just a convention. What's going to happen to the minus signs if I put them all in? They're going to cancel. So I'm not going to worry about the minus signs. So I have M, VR, I disk, plus I person, times omega. And so omega is little mvr divided by the total moment of inertia of the system. So let's put some numbers in. The mass of the person is 100 kilograms. The velocity of the person is 2 meters per second. And the radius is Sure, you could, but I'm not going to do it. I already started writing it out. And when you run this through, you should get 0.8 radians per second. Okay, so I need two volunteers. Somebody who doesn't mind being videotaped. Why don't you come down here? I need one more who doesn't mind being videotaped. You want to be sitting down or spinning?
I'll spin on there.
Okay.
Let's see if my hat gets knocked off. That'll make it extra entertaining.
Okay, start with your arms in. So I need somebody to come here and spin him. Who wants to spin him?
I could probably just kick my foot out and do it.
Yeah, just do it with these. So it just makes it more apparent. Okay, so I want you to spin him now. Long time ago, this happened. The student gave the person in the chair such a spin, she went flying out of the chair. So I don't want you to do that. Just give him a nice.
Be funny, bro. Go ahead.
Just a nice spin. Now bring your arms out. You increase your moment of inertia. Now angular momentum is conserved. Okay? Angular momentum is conserved. So as he brings the arms out, I just don't want you to get dizzy though.
Oh, good.
Okay. See, he's just, so really angular momentum is conserved. When he increases his moment of inertia, omega decreases. Okay, do you want to try it?
Sure.
Okay, so you take turn. Start with your arms in, not out. Because the other way is bad. Yeah, go ahead and bring your arms out and then in. How's that? Okay, so let's try one more. Is there a wheel over there? I didn't bring the wheel in? Oh, I didn't bring the wheel in.
That's really disappointing.
Yeah, let me go get the wheel. Okay, so just hold on to that. So I'm giving the wheel angular momentum. You have no angular momentum, but the wheel does.
Right.
Flip the wheel by 180 degrees.
That's hard to do.
Okay, let's do it this way. Let's do it this way. Maybe I should have started with the horizontal. Let me stop. Yeah, let me stop it like this. You go ahead and spin it. Now keep it horizontal. It might be easier. Yeah.
Oh, he moves. Do you want me to move like that?
No, I want you to be stationary. Okay, now put your feet on the stool and then flip that wheel. See, angular momentum is conserved. He's changing the angle. He's flipping the angular momentum of the wheel by 180 degrees. And because angular momentum is concerned, he ends up spinning. It's actually hard to spin that wheel, isn't it?
It is. It's hard to spin.
Okay. That's because it has angular momentum. It's like any object that has momentum, right? It requires a significant torque to rotate it. All right, thanks. All right, thanks, guys.
Because they're all like touching.
I'm sorry?
Because they're all touching.
Are they?
Touching the wheel and the touching the seat. Is that why?
Yeah, he's part of the system.
Okay.
Yeah.
So he flips it the other way, he starts spinning, and then he flips it back,
It goes back in the other direction.
and then he just stops, right? I guess he stops.
Yeah, well, he still has to turn. He has to still turned back to the original position, right? So he had no, the only angular momentum he had is the only angular momentum the system had is that of the wheel, okay? So let's say the angular momentum is L pointing upward. If he flips this down, now L points downward. He's actually changed it by a total of 2 times L. You need the total angular momentum to be L, so he has to spin in the opposite direction. Okay? Because angular momentum is conserved. So that's what that demonstrates. And also the one with the weights. Those are all conservation of angular momentum. So I'm going to do an example when I do the video for Thursday. Okay. I want to do one more thing. One last example. And it's not a long example. It's going to be with this wheel again. And I'm not going to advance the PowerPoint anymore. So I want to make sure I can see things in my video. Oh, I got to fix my video. Okay, it's fine. I need one more person to volunteer. Nobody else wants to volunteer? Or Evan or Dylan, you guys want to come down again? Okay. So I kind of want you to hold this kind of away from your body.
Okay.
I'm going to give this a spin. Like if I let it go, it just falls over, right?
Right.
So I'm going to give this angular momentum. Actually, I should have made it, I'm going to spin it this way. It's not that fast. And then I'll let it go. So hold on. It doesn't really fall over, does it? I didn't spin it fast enough. It doesn't fall over, right? Why doesn't it fall over? All right, thanks. Why doesn't it just fall over? And this has to do with when you ride what happens when you ride your bike. This is gyroscopic motion. All that happened is the object precessed, right? I'll have another device on Tuesday that spins better, okay? I can get it to spin a lot faster than that. This is an example of gyroscopic motion. So, let me draw a picture of what happened. Here's the wheel. The wheel was pivoted at this point. Let me make a bigger wheel. And I spun the wheel. I can't remember which way I spun the wheel.
Towards us.
Towards you. So omega pointed that way, right? So omega was this way. That means L was that way too. So L pointed that way. But you have the weight of this thing pointing downward. That means there's a torque acting on that wheel, right? Because of all that weight. You have a torque. Your R vector looks like this, right? You have R vector here and mg vector here. You point, oops, I had that backwards. Yeah, that's right. I have the R vector pointed that way and mg pointed down. Cross product is in which direction? Cross product is into the board, right?
Oh, yeah.
The torque vector is perpendicular to L. dl dt is our torque. In fact, I'll write it like this. Because the wheel has angular momentum, and because there's a torque into the board, the angular momentum has to change in the direction of the torque vector. Right? The angular momentum, the magnitude is not going to change. The only way the magnitude would change is if the torque vector was either parallel or anti-parallel to omega. And that's not the case. The torque vector is into the board. So it's going to make L change in that direction. It wants L to go from here to maybe here. So L starts this way and then points in this direction because L changed by a certain amount. Right? The torque vector causes L to change by a certain amount. This value and this value are the same. Okay? Let's make this angle be really small. Okay? So, what can I say there? What's delta L equal to? This is phi. These magnitudes are the same, and that's delta L. How are they related to each other? Well, this is not a problem is this is not a 90-degree angle, right? This is a really small angle. This is constantly changing direction. It's actually sweeping out a circle. So really this is an arc length. So delta L is L, I should call it delta phi, but delta phi is tiny. It's like an arc length, those changes. I divide both sides by delta t. Take the limit as delta t go to 0, and I get dl over dt equals L delta phi over delta t. Or I'm sorry, d phi dt. What's d phi dt? Yeah, and the problem is I got to differentiate it from this omega, right? And so I use a capital letter omega. It's the rate at which this is the rate at which it precesses. I know the wheel was crooked when we did the demo because I didn't spin it fast enough. But that was the rate at which it precessed. And so dl dt is this L, which is going to be I omega times big omega. But what's this due to? It's due to this torque mg times the magnitude of this vector. So we can actually solve for the precession rate. And that's the precession rate for that gyroscope. That's called a precessional frequency. That's the simplest gyroscope problem we can do. Because the gyroscope problems are in general complicated. This one is complicated. Why is it complicated? Well, the torque vector is changing the direction of L. Okay. The motion is complicated. And in reality, and I'm going to bring in a gyroscope next time, and I'm going to spin it fast. Not only does it precise like it, we can actually make it bob up and down, which we call nutations. And I'll say a little bit about that next time. Okay? So make sure you understand how to derive this equation. Okay? Any questions on this? So the video I'm going to make for Thursday, because I'm done, the video I'm going to make for Thursday is basically I'm going to do a bunch of problems for you, which for me is easier to make a video involving solve problems as opposed to talking about concepts. All right, so I'm going to stop here, and I'll see you guys